All right, what's up, guys? Just talking through the practice problems posted here. I typed in a lot of stuff already, and I'll just talk through it. So, as we learned in our first entry, a wave is just a disturbance that carries energy, and a medium is the matter that a wave travels through. An example would be air or water, whatever it's traveling through. Two categories of waves: we got mechanical, they require a medium; electromagnetic, do not. And the two types of mechanical waves, you have transverse and longitudinal, and that's what you see in these two examples. Here we have a transverse wave, and there you have a longitudinal. The difference being that in a transverse wave, the particles are moving up and down as the wave is moving left to right. Or if you imagine you just turn this as the wave goes this direction, the particles are moving this direction. So it's opposite or perpendicular. Two examples of transverse wave would be light. That's a really strong example in guitar strings. When I pluck a guitar string, it's moving up and down as the wave is moving left to right. Higher energy would be gamma ray. That's the most powerful electromagnetic wave that we got. A microwave is on that bottom end. Here we just have some vocab, so I'll just let you pause and look at these if you need to. Just double check your answers. I'm not going to spend time walking through each of those. Longitudinal wave, the particles are in the same direction. So here's the wave is moving left to right. Think about it as a spring compression. You get a compression and an expansion or extension called a rarefaction. But all of that's happening in the same direction that the wave moves. So two examples of longitudinal waves would be sound or a spring. Also seismic waves. Our example there as well. So for the waves that do not need a medium, I put right here, that'd be all electromagnetic waves. So I could choose any. I did gamma, infrared, and microwaves. So labeling the following point, remember wavelength, you can go crest to crest, trough to trough, or medium or midpoint to midpoint as long as a full wave passes. Crest is the top, trough is the bottom. Amplitude is the extension from midpoint to crest or midpoint to trough. And here, just as a side note, frequency is 1 over period, or period is 1 over frequency. So if I had a triangle, and if you want to add this to your notes, I would certainly try to do it. Where, remember, you cover whatever variable, frequency, period, 1 on top. Whatever variable I'm trying to solve for, I cover it up, and it says 1 over period. So frequency, if I cover it up, is 1 over period. And period covered up is 1 over frequency. So now we're coming back here. Jules listening to your favorite sound wave, which has a frequency of 440 hertz. And what is the period? That's what I'm solving for. So I'm solving for period. So covered up, it's 1 divided by frequency. So period is equal to 1 divided by frequency, which is equal to 1 divided by 440 hertz. And then when I do that math, what I end up with here, give me 2 seconds as I pull up my calculator. 1 divided by 440 gives me a period of 0.0022, or 23 is what it rounds to. And period is measured in seconds. So that's the label that you should have on there, seconds. Here, it's the same problem. I'm just solving for the different parts. So what is the frequency? But the period is 0.0039 seconds. So cover up period. Here I get 1 divided by frequency. Okay, so frequency is equal to 1 divided by period. That's 1 divided by period, which is equal to 1 divided by 0.0039 seconds, which is equal to 1 divided by 0.0039 is equal to 256. I'm going to round to the nearest whole. Frequency is measured in hertz. So if you can remember the big key to these equations, and always is, okay, can I identify what variables are given? And the big keys there is reading the problem or looking for labels. So 440 hertz, I know that's frequency. Seconds, I know that's period. And that's what we see right here. So wave speed is meters per second. The equation for wave speed we have right here. And just as we did before, you can actually create a triangle for that as well. And the way you do that is you have the two pieces that are multiplied end up going on bottom. So here I have frequency and I have wavelength or lambda. And then the part that's on top would be my wave speed or velocity here. So one way you could figure that out is if I cover up V, it's frequency times lambda, which is what I see right there. And then you have your units. So what do we use for frequencies? Hertz, wavelength, meters. Units for period is second. Okay. So in all of these now, I got wavelength is 15 meters, so that's lambda. And frequency is 0.100 hertz. So it's the wave speed. That's my question mark. So again, I would just go up here and I'd cover it up. Wave speed is equal to frequency times, and I got to copy paste this because there's not a key here. And so I just plug that in, and I'm going to get frequency 0.100 hertz times 15.0 meters, and that's going to give me an answer of 1.5, and it's wave speeds, that's meters per second. Okay. Here I got a wave speed, oh, what happened? There we go. Wave speed of 340 meters per second. What's the wavelength? That's what I'm trying to solve for. If frequency is 220 hertz. Okay, so now I'm solving for lambda, so I'm going to go up to my triangle again, cover it up. I get V over F. So lambda is equal to V divided by F, so wave speed divided by frequency. Wave speed is 340 meters per second divided by frequency, which is 220 hertz, which is equal to 340 divided by 220, 1.55. And it's lambda, so that's meters. This one, I got a frequency of 440 hertz. It's an A note on a musical instrument. Wavelength of 1.5 meters. And what is the wave speed? That's what I'm solving for. So I go up here again, I cover up V. It's F times lambda, frequency times lambda, which is actually the same as this one. I'm just going to copy here, save some time. Okay, which is equal to frequency 440 hertz times 1.5 meters is equal to 660 if my mental math is right. Yep, 660 meters per second. Almost done, only got a few more problems here. So speed of sound in air. Oh, that's the same problem. Lucky. How did I not notice that? Whatever, you just get to skip it. Okay, so energy, you got Roy G. Biv is our visible light spectrum. Red is the lowest energy. Violet is the highest energy. Doppler effect, as the source comes towards you, the pitch gets higher because the frequency is getting higher, and the pitch gets lower as it moves away as they get spread out. So think about Sheldon from the Big Bang Theory clip. So, two astronauts are floating in space without a radio. There are no radios. If one screams, will the other hear it? Now remember, in space, there is no matter. Okay, it's a vacuum. Okay, sound waves are mechanical waves. And what I have to remember is, do mechanical waves require a medium to do these things? And the answer is yes, sound waves require a medium. So that means that the sound would not transfer to the other astronaut. Doesn't have a medium. No. So this one, just popping back, I got a period of 6 seconds, and it says with frequency, so I include this one at the end just so you could get in the habit of saying, okay, what are my givens, right? Identify your givens. Frequency is what I'm solving for. What is the frequency? Period is 6 seconds. I have a known and I have an unknown. So I go back up to my triangle up here, and you cover up whichever variable you want. And frequency covered up is 1 divided by period. So frequency is equal to 1 divided by period, which is equal to 1 divided by 6 seconds, which is equal to 1 divided by 6 is 0.17 frequency hertz. And well, let me know if you guys have questions, send an email or ask.